We have been teaching pretty much the same way for 200 years. We are teaching the way we taught at the beginning of the Industrial Revolution. We wanted our students to invent cotton gins, steam engines, the telegraph, the telephone, automobiles, airplanes, computers, and spaceships. But we can't afford to continue to teach in such a tightly focused manner. The world has become too complex, has too many difficult problems, and is changing too quickly. We need inventors who can combine computer chips, genome sequencing, and DNA detection, and build machines that can diagnose disease. We want inventors who will combine microprocessors invented 20 years ago with the Stirling engine invented 200 years ago to solve the world's energy problems. This kind of revolution will come only from those who are expert in many different and diverse disciplines. And these people can't just be inventors. They need to inspire and lead and sell their inventions. They need to be able to quickly get their ideas across. This suggests remarkable people who are extremely open to new things and extremely persuasive and extremely flexible. We can't develop folks like this by talking to them for 4 years. One way to change our way of teaching to meet the 20th century world is to start using more modeling teaching. Modeling has been done in the high school physics community for over 5 years and is proving to be highly successful. A few teachers are experimenting with modeling in the humanities with some impressive results. Modeling greatly increases retention, builds minds that are comfortable with change, and fosters widely diverse thinking. Do we know why modeling works? Certainly not completely, but we think there are some good brain cognition, brain science reasons for why it works. The explanation seems to involve where new information is stored in the brain. There are 2 major areas of storage in the brain: the language area and the spatial area. When we teachers deliver material to our students, the students absorb the material by listening, hopefully, or by reading. The material goes into the brain through the eyes and ears to the language part of the brain. Unfortunately, the language part is not the best part for retention. Studies have shown that if we can deliver the material down to the spatial part of the brain, we will get much more retention. We want to get our new teaching in through the eyes and ears and then down to the spatial part. And here's a very important element. Once the information is in the spatial part of the brain, we want the students to move the information back and forth between the spatial part of the brain and the language part. This translation, or mapping, by the student apparently greatly increases the student's understanding and thus their retention of the information. Brain scientists call this interface between the language and spatial part of the brain the Conceptual Structure Spatial Representation Interface, or CSSR. So how do we get the material into this spatial part of the brain? We do it with a method of teaching called modeling instruction. But isn't this just inquiry-based learning that we've been experimenting with for 50 years? Isn't this just constructivism as promoted by Jean Piaget with emphasis on student collaboration? Isn't this where student learning is enhanced by students teaching each other, their use of kinesthetics, the small settings, and just new classroom arrangements? Well, modeling instruction is inquiry-based, and it often uses small whiteboards, and modeling benefits from the inquiry, mentoring, and student collaboration. But modeling instruction has some additional elements beyond the inquiry learning that has been around for a while. The difference is that with modeling, the students build their own tools from which they do the inquiry, and these tools become an intrinsic, fundamental part of their understanding of the subject. And a very important thing has to happen during the modeling: the movement of information in the brain through the CSSR interface. How is modeling different from regular teaching? Let's look at how a physics lesson introducing Newton's second law might be done the conventional didactic way. The teacher would probably spend some time explaining Newton's second law, i.e., force equals mass times acceleration. The teacher might introduce some other formulas showing how the distance an object moves can be calculated from the acceleration, the initial velocity, and the initial location. After some discussions, the students might do some experiments in the lab with some weights and a spring scale. After some more experiments, the students would put some data into a table and plot some points on a graph. Eventually, the students would authenticate the teacher's formulas. Teaching Newton's second law using modeling instruction is different. The teacher does not give a formula or try to impart any authority-driven formulas. Instead, the students are asked to develop the relationship between the forces applied to a mass and the movement of a mass. With a modeling lesson, the students might start out in the lab with some masses, a spring, scale, maybe some dry ice blocks to reduce friction. They would not be given any formulas beforehand. Instead, they would be asked to discover the relationships between the forces, masses, displacements, and velocity. The students might take some measurements with one mass, then add some more mass, and find the relationships by entering numbers into a table and plotting points. Eventually, they would discover some proportionalities between the force and the mass. More lab work would eventually reveal all of the relationships between force, mass, acceleration, velocity, and distance. The important goal is to get the students to discover the relationships themselves, take ownership, feel the mass and its velocity. The information coming into the brain is no longer going through the language areas, it's going into the spatial part. It may seem very similar to lab-based inquiry session, only run backwards. But it's the backwards part that makes the modeling work. The students, instead of authenticating the teacher's statements, are building their own authority. Well, it's pretty easy to understand how modeling might work in a class like physics. But what about other disciplines? What about history? What about English? History is hard to teach in a lab environment. Students can't experiment and arrive at relationships like they can in physics. So we tend to teach history by telling our students what has happened. And we tend to tell it serially, chronologically, because that's the way it played out. But teaching history serially keeps the information in the language part of the brain, because it teaches history in a non-intuitive way that connects things chronologically and encourages or requires memorization of dates and lists. Why can't we teach history like we do physics, with forces and energy concepts that the students develop tools to work with? Suppose we wanted students to approach a subject in history and come up with some tools to explain what happened by looking at the forces that shaped that time in history. For example, let the students look at the westward movement of people across the United States in the middle of the 19th century. We might break the students up into small groups, give them small whiteboards and markers, and ask them to come up with some generic tools to explain how the railroads expanded, why cities form, how different innovations influence the movement. One group of students might develop one set of forces explaining the movement. Another group might choose a different set of tools. Several cycles of students exploring the westward movements and the relationships between the forces of history and demonstrating the results to each other might lead the whole class to come up with a common set of tools that covered most of the separate groups' findings. One recent series of history modeling exercises resulted in a set of tools that the teacher mnemonically labeled SPICE for social, political, intellectual, cultural, and economic. Once these tools were developed by the students and applied to a period in history, the students could begin to use the tools to other times in history where similar movements occurred. These tools could be used to show the forces shaping movements from Europe, resulting in the colonization of Africa, or to explain the movements across Australia by early man, or the movements by Mongols across northeastern Asia, and Persians, and Polynesians. Now that the students have a set of tools that show the forces shaping history, might they apply them to other events in history? We're at the beginning of experiments with modeling in the humanities. We will probably never refine modeling in history and English as well as it has been done in physics, but we're seeing high school students develop very sophisticated analytical skills not normally seen before graduate school. We think that more work in modeling instruction in humanities will result in better defined techniques and more knowledge about what works and what doesn't.